part for today, I want to talk about this position correction step that I alluded to before a bit. Yeah, so let's look at the impulse step again. So as mentioned just earlier, we're computing these impulses to remove the unphysical negative relative velocities that move our bodies into each other, right? So if we have this configuration, negative relative velocity, the impulse definitely cancels that out and potentially pushes the objects out. However, as shown in this picture, right, that's the state we had. We had objects that were in each other potentially due to the discrete larger than zero time step. For a bit here on the slides, I hope you can see it, right? There's a small piece where they actually overlap. And now we compute our impulse. The velocities are okay, but the objects are still in the state. They are still in a state that would never happen physically and in reality, because the objects cannot just pass through each other, right? In a way, obvious solution is, well, let's not just correct the velocity, but also the configuration, the actual position of our bodies. Sounds great on first sight, but there are actually quite a few pitfalls with that, and that's what I want to discuss a bit in the next steps. So, also as a warning, this is now in a way an extension that you often need to get a good result for something like a virtual game. It's definitely less physical. The impulse has a very sound foundation, but this position correction step is really more of a fix-up, as you'll see. Yeah, so there are a few different possibilities that we have. So if we have something like a sphere moving along, colliding with this box here, one obvious solution would be to just project it into the free space around the object it's colliding with, such that it doesn't intersect. Right, so for the sphere it's actually quite obvious and works nicely. How about this box? If we end up in this state, we can also move it out. Still looks good, probably. It's better than this colliding state, but as you can see here, we basically just moved a small part. Now we actually shifted the box by a large part of its volume. So here the distance is not very big, but this is a pretty big change to the state we actually computed. And there are more variants that you could do. How about actually stopping the motion, right? You could, I think a relatively obvious idea is also, if we have this motion, our box here is actually moving along the path, why do we keep on going? We could try to actually find out where does it start colliding, where does it go bad, and then we can basically stop the object there, for example. But in this case already you can see in these tangential motions, again the distance is not so large, but it would actually keep our object moving from most of the way towards the target state. Yeah, so what turns out to be a preferable solution is to actually use all the framework we have so far, and in such a state like the gray one here at the end, maybe move the object a bit in terms of its position, but also rotate it such that we don't need to displace it so drastically, but as much as possible stick to the actual position that we computed. And that's a bit what I want to discuss in the following. So for that to work, we also need to take into account the mass. Right? In the previous example with this big box and a small object colliding with it, if we don't pay attention, we treat them equally, we might displace this large object by some distance due to a collision with a tiny one. That doesn't make sense, right? It makes sense to treat it like an impulse and take into account the relative masses of the pair. So a heavy object should move much less than a lighter one. want to use the translation and rotation and move as little as possible. So again, coming back to impulse, what we can do here is now that we actually apply an impulse. So here, this should look familiar now. This is the same old to before. The whole, for a pair of objects A and B, the whole linear and rotational parts of the impulse along some normal. Now it's not a normal of a collision, but now we have a geometric interpenetration of the objects, and along this direction we're now computing the impulse, and we're taking into account how far the objects have moved into each other, this distance d here. And now the nice thing is, if we compute an impulse like that just from the distance, we can directly apply it in line with the impulses before and get this update that respects the masses. So this does work quite nicely for the linear part, for the position in this case. So notice that this is now the big difference here. Instead of applying it to velocity, here we are now changing the positions of the objects directly based on an impulse computed for this distance t. Yeah, so for the angular component, it's along the same lines, but slightly more complicated. So the angular component of such an impulse is given by this expression. So here we have some impulse j acting along the normal, right? And then from the impulse equation, this is the whole effect it has. So remember, now our goal is not like before to just change the angular velocities, but now we want to actually update the orientation of the object. So if we apply that at the point of collision, then we'll actually get an angular motion by this impulse at a collision time point, again weighted by the inertia tensor. And this is basically what we can now directly use to update our orientation R, with the only change that now we're actually weighting this component, right? This was the influence here. We're weighting this by the effect it had in terms of this of the original impulse equation. So this is in a way the main change here, that we're weighting it differently to take into account the effect it has in our original calculation. Yeah, there are some slight changes or parts to be aware of. If our time step was too large, like shown here at the top, and the object is, for example, worst case, fully inside, then we shouldn't start trying to change this orientation, because here we would probably spin the object a lot, but there's no chance, it's not going to help, right? So we need to somehow limit it a bit. And also in this case, if I have this box and I try to move it up here, it will very quickly collide on the other side. So I need to be careful applying this update, and a bit like collisions, take into account the environment. So what also the Millington book recommends is that we basically limit the amount of update for the orientations, only allow small corrections here. So what the heuristic they recommend is basically we can do that proportional to the relative collision point on the object. That's in a way a geometric measure, and gives us a distance, and then applies updates on the order of that distance where the collision was detected. Yeah, and just to highlight another effect that can happen here, if we have a state where the objects are in each other, and we update repeatedly, we might actually move an object out of each other, right, from this initial configuration to one where they rest on each other, and then they might start to topple. Similarly, if we have objects on slopes, on inclined grounds, and we start adding these position correction steps, then we can actually start to make the object slide, and there are other unintended side effects of this. In a way, that is the cost or the price we pay for fixing these unphysical configurations. So you could also try to live with such a state and then make sure that the objects in subsequent time steps go out of each other and no one notices, or if you instantly in the current simulation step want to ensure that we have a physically valid state that we can nicely display, then this is actually a relatively straightforward and relatively safe way to prevent that, with the aforementioned problems that we might we actually need to limit the corrections, and it might lead to some side effects basically, but at least these hopefully are not as obvious as these clearly unphysical interpenetrations of objects. Yeah, that's all for today actually, and then next week I want to discuss a bit how to include this correction step into a kind of engine-like simulation update, and then also discuss a bit some tweaks that you typically include in such a simulator. But so far for now, goodbye.